Welcome to The Explainer. Today, we're going to dive into the invisible world that's all around us, the world of gases. We're going to unpack the elegant physics that governs literally everything, from the air in a diver's tank to the atmosphere of a whole other planet.
So let's start with a question. What could your car tires and a hot air balloon possibly have in common? I mean, it seems like a weird question, right? One is all about containing pressure, the other is about rising with heat. But the answer is that they both run on this hidden and honestly surprisingly simple set of rules that all gases follow. We're going to explore what those rules are and, way more importantly, why they even exist. Okay, so to get our heads around this, let's start with the world that we can actually see and measure. Long before we could even imagine individual molecules, physicists were watching how gases behave, and they literally wrote the rulebook. And here's rule number one, Boyle's law. Just think about pumping up a bicycle tire, right? As you push that handle down, you're shrinking the volume of air inside the pump, and you can physically feel that pressure just shoot up. It's this simple, super intuitive relationship. As one goes down, the other goes up.
And what's so cool is that the math behind it is it's beautiful in its simplicity. For that air inside the pump, as long as its temperature stays the same, the number you get when you multiply its pressure times its volume never changes. It's a constant. So if you cut the volume in half, the pressure has to double. It's a perfect balancing act.
Okay, so what happens when we bring temperature into the mix? Well, Charles's law explains why a balloon you left in a hot car looks like it's inflating all by itself. As the temperature of the gas inside goes up, its volume has to expand, and it pushes the balloon outwards. And again, the relationship is just incredibly elegant. The ratio of a gas's volume to its absolute temperature is constant, as long as the pressure isn't changing. So if you double the temperature, and we're talking absolute temperature here in Kelvin, you literally double the volume. It's that direct.
Now this is the reason you see those big warnings on aerosol cans telling you not to throw them in a fire. If the volume can't change, like in a sealed can, heating the gas inside makes the pressure climb and climb and climb to really dangerous levels. It's also why your car's tire pressure is always a little bit higher after a long drive on a hot day.
And you're probably starting to see the pattern by now, right? Just like with Charles's law, we have another direct, constant ratio. When the volume is locked in place, pressure and temperature are basically tied together. They have to rise and fall in perfect sync. And believe me, the rule book keeps going. There are laws for how gases mix, how they move, how you count them. But all of these laws, all these incredibly reliable observations, they all lead to this one big, nagging question. Why? Why on earth do gases follow these rules so perfectly? Well, to find that answer, we've got to zoom in, like way in. We need to shift our perspective from the macroscopic world of pressure gauges and thermometers and go down to the microscopic world of these frantic, invisible little particles. And here it is. The answer is something called the kinetic theory of gases. And folks, this is the master key that unlocks the whole thing. This theory completely reframes the problem. It tells us to stop thinking of gas as just a substance. Instead, imagine it as this colossal number of tiny, frantic particles, all in constant, chaotic motion. So let's really dig into the energy of these little particles, because what we experience as heat or temperature in our world is actually just a measurement of how fast these tiny particles are buzzing around. It's their kinetic energy. We can measure this kinetic energy in a few different ways, but take a look at these formulas. Look closely. Do you see the one thing they all have in common? It's that big letter T for temperature. Temperature isn't some vague, abstract property. It is a direct measure of the average kinetic energy of all those gas particles. More heat simply means faster particles. Now, this is where it gets really, really cool. The actual shape of the gas molecule changes things. See, a simple gas like helium is basically a tiny little sphere, like a billiard ball. It can only move back and forth, up and down, side to side. That's 3 degrees of freedom. But a molecule like oxygen is shaped more like a tiny dumbbell. So not only can it move around, it can also tumble and rotate. It has more ways to hold and store that energy.
All right, we've got all the pieces on the board now. We've seen the big picture rules, and we've seen the tiny little particles whizzing around. Now, it's time to connect them. This is the aha moment. This is the big reveal. First, we need one new concept, but don't worry, it's simpler than it sounds. It's called energy density. It's basically a fancy term for a really simple idea. Just imagine a box. 1 cubic meter in size, filled with air. The energy density is just the grand total of the kinetic energy of every single particle buzzing around inside that box. It's just how much motion energy is packed into a space.
So what, right? I mean, who cares about the energy of these tiny particles? What does the random, chaotic buzzing of trillions of molecules have to do with the steady, constant force that we can actually feel? The force that inflates a tire or holds up a hot air balloon? And here it is, the answer, in one of the most profound and stunningly simple equations in all of physics. Pressure is simply 2/3 of the kinetic energy density. They aren't just related. On a fundamental level, they are two different ways of measuring the exact same thing. Just let that sink in for a second. The force you feel from the wind or when you push on a balloon, that is the collective, relentless smack of trillions upon trillions of tiny molecular collisions. So when you really think about it, Boyle's law and Charles' law, they're not really rules at all, are they? They're just the unavoidable, large-scale results of the laws of motion and energy playing out on a microscopic scale. And this connection, this incredible bridge between the tiny world of particles and the huge world we see, it reveals something truly profound about the universe. It shows us that often concepts that seem totally different are actually just different faces of the same fundamental idea. You know, in the language of physics, when you break things down to their most basic components of mass, length, and time, things like pressure, energy density, the stress inside a steel beam, and even a material's stiffness, they all share the exact same fundamental identity. They are all, at their very core, just different flavors of energy packed into a certain volume. So, think about the journey we just took. We started with a simple car tire, and we ended up with a fundamental truth about the nature of energy itself. It proves that by understanding the world of the incredibly small, we finally unlock the secrets of the incredibly large. And it just makes you wonder, doesn't it? How many other massive secrets of the universe are hiding right there in plain sight, just waiting for us to look at the world from a different angle?